Dear children, in this session we will be discussing modulus and conjugate of a complex number. Till now we have learnt what complex numbers are and we have discussed the algebra of complex numbers, how they can be added, subtracted, multiplied or divided. Let us see what is meant by modulus and conjugate of a complex number. First we'll see how the geometrical representation of a complex number can be done. Now suppose we assume x dash ox and y dash oy to be any two rectangular x's in this plane. Then you will find corresponding to every point P on this plane there will be a unique ordered pair of real numbers which is normally let us say if it is denoted as an ordered pair x comma y, then x will be the x coordinate or abscissa of the point P and y will be denoting the y coordinate or ordinate of the point P. Now this point P with x as abscissa and y as the ordinate is said to represent the complex number z, which is denoted as x plus iota y. Now this representation of complex numbers, this kind of representation of any complex number as points in a certain plane is termed as Argand diagram, and this plane can be termed as complex plane or an Argand plane. Now this term x-axis, if you see in this plane, the x-axis is the real axis and y-axis is the imaginary axis. So imaginary numbers, imaginary part of the complex number will be plotted along the y-axis and the real part along the x-axis. Now the length OP, if you look at this diagram, P is a point with abscissa x, y as its ordinate, and in terms of complex number, it is denoting a complex number with real part x and imaginary part y. So it is denoting the graphical representation of a complex number x plus iota y. That means the distance from O to this point, which is the foot of the perpendicular, is x unit, and let us assume this point is M. From here to the point P, the distance is y. So if you see, this is forming a right angle triangle, and applying Pythagoras theorem, the hypotenuse OP, it comes out to be square root of x square plus y square. So children, the length OP is called the modulus of the complex number, which is denoted as x plus iy, and its notation is mod of z. Modulus function we are aware of. So mod of x, which can be written as mod of x plus iota y, will be denoting the line segment OP, which we saw comes out to be square root of x square plus y square using the Pythagoras theorem. Now coming to the conjugate of the complex number, if the complex number is denoted as x plus y iy, then another complex number of the form x minus iota y is termed as its conjugate. So both these complex numbers are conjugate of each other. And how they differ? Their imaginary parts will differ by a negative sign. The sign of imaginary part will be different in the conjugates which are denoting complex numbers, which are denoting the conjugate of each other. So if z is your given complex number, then z with a bar over it is conjugate of it, and you will see their real parts are same and their imaginary part differ by a negative sign. This is the notation for conjugate of any complex number. The complex number with a bar will be its conjugate. Now let us do some calculation based on this. Now we know the notation for the modulus of a complex number and its conjugate. So let us come to a result. Say z is your complex number, then its multiplicative inverse, you must have seen while doing the algebra of complex numbers, we saw multiplicative inverse of a z can be denoted as z with exponent minus 1, or we can write it as reciprocal of the complex number. Now because z is x plus iy, so its reciprocal will be 1 over x plus iy. Now multiplying this complex number with its conjugate and dividing with the same, we can simplify multiplicative inverse. So when we multiply this complex number with conjugate of z and we divide it with conjugate of z, it reduces to the numerator is x minus iota y and the denominator takes the form x square plus y square. Now if you look at the numerator, this is nothing but conjugate of z. And if you look at the denominator, it is square of the modulus. So what do we see? 1 over z, which is multiplicative inverse of z. It is coming out to be conjugate of z divided by square of its modulus. So multiplicative inverse can also be evaluated using this expression. Now if we take cross multiplication on both the sides, we find z multiplied with its conjugate is equal to square of its modulus. Children, if you will find the modulus of conjugate of z, see if the modulus of z is square root of square of real part plus square of imaginary part, then in its conjugate you will find real part is x but the imaginary part is minus y. So when we find its modulus, it will be square root of square of x plus square of minus y, and square of minus y comes out to be y square only. So you will find modulus of a complex number and its conjugate, they both are same. So we get a result which is z into its conjugate will be equal to square of its modulus. Now discussing some properties or results which involve modulus and conjugate of a complex number. Say we have two complex numbers z1 and z2, then modulus of product of z1 z2 can also be written as modulus of z1 multiplied with modulus of z2. So either you multiply both and then you take their modulus, or you first evaluate their modulus and then multiply them. The result will be same. In the same manner, if you are dividing complex number z1 with z2 and you are reducing it to a new complex number and then you are taking its modulus, or you are dividing the modulus of z1 by the modulus of z2, they will reduce to the same complex number. The condition over here which is to be met is mod of z2 should not be equal to 0. That will happen if z2 is not 0, then its modulus will not be 0. Okay. Now moving on to the third one. This is conjugate of product of z1 into z2. If you see for two complex numbers z1 and z2, if we multiply them first and then take their conjugate, or we multiply their conjugates, the result holds on both the sides. It comes out to be same. So you can go for multiplying them and then taking the conjugate of the resulting complex number, or you can take conjugate of both the complex numbers and then multiply them. The product will come out to be same. The resulting complex number on both the sides will be same. Next one says if two complex numbers are added or subtracted and converted into a new complex number and then its conjugate is taken, then it will be same as the sum or difference of the conjugates of these two complex numbers. Now that holds for division also. Whether you are dividing complex number z1 with z2 and after evaluating the new complex number, if you define its conjugate, or you divide conjugate of z1 with conjugate of z2 and reduce it to a new complex number, both will come out to be same, provided complex number z2 should not be equal to 0.